Cylindrical coordinates in 3 space. So the cylindrical coordinate of a point P in 3 space are coordinates of point P in 3 space are r and theta and z. So if you take point in Cartesian 3 space x, y, z, and you want to convert it to r theta z, the z stays the same. Then you basically drop a perpendicular from the point P onto xy plane, and then find the polar coordinate for that point on the xy plane. That would make r and theta. So r and theta are the polar coordinates of the projection of P onto the xy plane. Z is the same as in Cartesian coordinates. In cylindrical coordinates, we usually assume r is bigger than equal to 0. So this is we're starting to get to the point that we're assuming r is bigger than 0, bigger than equal to 0. So the conversion between cylindrical and Cartesian is very similar to the conversion between polar and Cartesian. So converting, if you're converting from cylindrical coordinates to Cartesian coordinates, x again is r cosine theta, y is r sine theta, and z is z. If you're converting from Cartesian to cylindrical, r squared is x squared plus y squared, and tangent theta is y over x, and z is equal to z again. Example: convert the cylindrical coordinates, a cylindrical point r and theta and z into r theta and z equal to 2 and negative pi fourth and 1 to Cartesian coordinates. So r is 2, theta is negative pi fourth, and z is equal to 1. Z stays the same. To find x, you use r cosine theta, and to find y, you use r sine theta. So 2 cosine of negative pi fourth is square root of 2. 2 sine of negative pi fourth is negative square root of 2. And the Cartesian coordinates is going to be square root of 2, negative square root of 2, and 1. Let's convert the other way around. Let's convert the Cartesian point x, y, z equal to negative 2 square root of 3 and 1 to cylindrical coordinates. Z is going to stay the same. Z is going to be 1. To find r, negative 1 to power 2 plus 2 square root of 3 to power 2 is going to be r squared. And tangent of theta is going to be 2 square root of 2 square root of 3 over negative 2, which is negative square root of 3. So r is 4, and tangent of theta is equal to negative square root of 3. And so what I know to find theta itself, you have to know a little bit more knowledge. And from here, I know that x is a negative value. So what I find for by plugging in this, by using arctan, I find negative pi third. And so I have to add pi third to get theta equal to 2 pi third for the angle. So 4, 2 pi third, and 1 are the is the cylindrical point. Now describe this, another example, example 4, describe the surface given by the equation in cylindrical coordinate, and the equation is z equal to square root of r squared plus c squared. So how do we we are familiar with the Cartesian from look of this looks like a quadric surface, but we're familiar with the Cartesian quadric surfaces. So let's see if I can convert. So this is going to be still z. R squared is going to be x squared plus y squared plus c squared. Again, this seems like to be part of a quadric surface because it's only positive here. Let's go to power 2 anyway to recognize this a little better. Put these two together, take the other one to the other side. So from here, I know that z squared has to be bigger than c squared. And this is one of those three quadric surfaces between a cone, elliptical, hyperboloid, and of one hyperboloid of one sheet or hyperboloid of two sheets, and which one it is. And so since there for some z values there's no x and y value, it's hyperboloid of two sheets. And so but it's hyperboloid of two sheets, but again you see that there's only positive in here when you go to power 2, you actually, the hyperboloid of two sheets has two sheets, but we only use the upper part. So this is upper piece of the hyperboloid of two sheets, and the original equation only describes the top sheet. And the bottom sheet would have been z equal to negative square root of r squared plus z squared. And so this is the picture again, and you can see that this is the top part is this equation, and the bottom part is this equation. Example 6. Describe the solid region shown below using inequalities in cylindrical coordinates. It's cylindrical coordinates, so it makes sense that we describe cylinders using cylindrical coordinates. And actually, it's not quite unrelated. A lot of times when you see cylinders, you tend to use cylindrical coordinates. So in here, what I see is cylindrical coordinates has 3 coordinates, right? Here I see the bottom part is z equal to 0, the top part z is equal to 3. So z for this one is between 0 and 3. Also for that one. Now, what else do we know? And here it goes all the way around. So theta does one full round. Theta is between 0 and 2 pi. But how about the other one? Is this 0 to 2 pi? No, theta it actually sort of starts from over here, which is negative y value, and goes all the way to pi half, which is right here. And so this one is negative pi half for theta. So theta is between pi half and negative pi half. For this one, R is, so in here, R goes, and when you're inside the cylinder, R is less than 2, but when you're on the boundary of the cylinder, R is equal to 2. So R is between 0 and 2. And here also 0 and 2. Again, R, when you're inside the cylinder, let's say in this point, R is definitely less than 2. But on the boundaries of the cylinder out here, R is equal to 2. So this is actually a good exercise, and you can practice on it to realize how the cylindrical coordinates